Hello and welcome. Today, we will be taking a deep dive into the heart of modern Hadoop, the YARN architecture. This presentation, titled Hadoop YARN Architecture, a complete overview, will provide a comprehensive understanding of yet another resource negotiator. We'll explore what it is, why it was necessary, how it works, and its profound impact on the big data ecosystem. Let's begin. YARN, which stands for Yet Another Resource Negotiator, is a fundamental component introduced in Hadoop 2.0. Think of it as the sophisticated connective tissue that sits between diverse applications and the core Hadoop distributed file system, HBase. Its primary role was to transform Hadoop from a system dedicated solely to MapReduce batch processing into a truly general-purpose, large-scale data operating system. Essentially, YARN functions as a distributed operating system for big data workloads. Its key responsibilities include intelligent resource allocation across the cluster, job scheduling, and enforcing quality of service policies. The development of YARN was driven by significant limitations present in the original Hadoop 1.0 architecture. First, scalability was constrained, with practical limits of around 4,000 nodes and 40,000 concurrent tasks. Second, availability was a major concern because the single job tracker component represented a single point of failure, or SPOF. Third, resource utilization was inefficient due to static map and reduced slots, preventing dynamic allocation. And finally, it only supported the MapReduce programming model, limiting the framework to batch processing alone. YARN elegantly addresses each of these limitations. It enables enhanced scalability, supporting clusters of over 10,000 nodes and more than 100,000 tasks. It improves availability through built-in support for Resource Manager high availability. It allows for better resource utilization by employing dynamic containers that are allocated on demand. Crucially, YARN is multi-engine, supporting modern processing frameworks like Apache Spark, Apache Tez, and Apache Storm. And it maintains backward compatibility, allowing older MapReduce version 1 applications to run without modification. YARN operates on a master-slave architecture. Its core components are as follows. The Resource Manager, or RM, acts as the master daemon, one per cluster. The Node Manager, or NM, is the slave daemon, running on every single node in the cluster. Each application has its own dedicated application master, which manages its lifecycle. Resources are encapsulated in units called containers. Finally, client tools are used for application submission and monitoring. The Resource Manager is the master daemon and holds the ultimate authority for resource management in the cluster. Its main responsibilities are to track the health of nodes, schedule applications, and allocate resources. It contains two key subcomponents: the scheduler, which is purely responsible for allocating resources to running applications based on a policy, but it does not monitor or track application status. And the Applications Manager, which handles job submissions, negotiates the first container for an application master, and restarts the application master container on failure. The Node Manager runs on every individual data node in the cluster. It is responsible for monitoring the health and resource usage of its node, reporting this status back to the Resource Manager via regular heartbeats, and managing the lifecycle of containers assigned to it. Its functions include container authentication, load management, and close monitoring of resource consumption like CPU and memory for each container. Critically, there is one application master per application. This is a unique and powerful concept. The application master is framework-specific, meaning a MapReduce application has a MapReduce specifica M, and a Spark application has a Spark specifica M. Its job is to negotiate appropriate resource containers from the Resource Manager. It then manages the entire lifecycle of the application, monitors its progress, and requests containers from node managers to execute the actual tasks. A container is the fundamental unit of allocation in YARN. It represents a bundle of resources on a specific node, including RAM, CPU cores, and disk space. Containers are allocated dynamically based on the application's current needs. They are launched via a Container Launch Context, or CLC, which is a specification that includes environment variables, security tokens, any necessary dependencies, and the actual command to be executed to start the task within the container. This diagram visually summarizes the interaction between all the components we've just discussed. The client submits an application to the Resource Manager. The RM then works with the Node Manager to launch the application master for that job. The application master, in turn, registers with and negotiates resources from the RM. Once resources are allocated, the AM instructs the node managers to launch containers. Finally, the tasks are executed within those containers. The diagram clearly shows this flow of communication and control. Let's walk through the complete workflow step by step. Step 1. A client submits an application to the resource manager. Step 2. The RM allocates a container and instructs a node manager to launch the application master for that application. Step 3. The application master registers itself with the resource manager. Step 4. The AM negotiates for and requests additional containers from the RM for its tasks. Step 5. The resource manager instructs the node managers to launch the requested containers. Step 6. The application code executes within the containers. Step 7. The client can monitor the application's progress through the RM or AM. Finally, upon completion, Step 8. The application master unregisters with the resource manager and shuts down, releasing its resources. YARN supports pluggable scheduling policies. The first in first out, or FIFO, scheduler is simple but not suitable for shared clusters, as small jobs can get stuck behind large ones. The capacity scheduler organizes resources into hierarchical queues owned by different organizations. These queues are elastic and can borrow idle resources from others. The fair scheduler aims to balance resources so that all applications get roughly an equal share over time. It supports preemption to enforce fairness and the dominant resource fairness, or DRF, algorithm for multi-resource environments. The adoption of YARN brings numerous benefits. It provides unparalleled flexibility by supporting multiple data processing engines in the same cluster. It enables highly efficient resource management through dynamic allocation. It offers massive scalability, managing thousands of nodes. Performance is improved with a centralized and specialized resource manager. It enables multi-tenancy, allowing secure sharing of the cluster among many users. And it incorporates robust security using Kerberos, SSH, and secure transmission protocols. While powerful, YARN does have some limitations to consider. Its architecture introduces complexity, leading to configuration and management overhead. There is a slight performance overhead and added latency compared to a dedicated, single framework cluster. Without high availability configure, the resource manager remains a potential single point of failure. Furthermore, its native support is primarily focused on the Java ecosystem, which can present integration challenges for other languages. To successfully manage a YARN cluster, follow these best practices. Carefully configure resources to balance the needs of YARN and other running services on the nodes. Implement consistent monitoring using the resource manager's web UI. For log management, configure log aggregation to push all container logs to HDFS for easy access. Choose your scheduler wisely based on your organization's workload and sharing model. And finally, never overlook security. Implement Kerberos for authentication and strict access controls. YARN's multi-engine support powers a vast ecosystem of real-world applications. For batch processing, it runs MapReduce. For interactive querying, it supports Apache Tez. For stream processing, it can manage Apache Storm applications. For in-memory processing, it is the foundation for Apache Spark jobs. For graph processing, it runs Apache Giraffe. And even distributed NoSQL databases like Apache HBase can run as YARN applications for managed deployment. In summary, YARN is the cluster resource manager that fixed the critical limitations of Hadoop 1.0. It is built on a master-slave architecture comprising the resource manager, node managers, and per application masters. It supports multiple scheduling policies to fit different cluster needs. Most importantly, YARN transformed Hadoop from a single-purpose batch processing system into a versatile, multi-purpose data platform that is essential for modern enterprise big data processing. This concludes our overview of the Hadoop YARN architecture. Thank you for your attention.